Today our focus is on operational excellence, achieving zero fluctuation and daily stability in blast furnace iron making. The blast furnace process is inherently complex, yet it boasts exceptionally high availability, typically exceeding 95% of the time available. Our strategic goal is maintaining this stability, which is essential for achieving the high efficiency and advancing goals like energy saving and uh, CO2 reduction. Now, exceptional process stability is absolutely mandatory for maintaining high efficiency. A stable operation is defined by the correct fuel input and consistent product quality. The stability of operation is visibly reflected in the product chemistry. Crucially, the hot metal silicon content should fluctuate only minimally, with fluctuation generally controlled to within plus minus 0.15%, and this figure can sensitize us that what sort of fluctuation is desired. Now, fluctuation in inputs or output lead directly to instability and inefficiency. Therefore, the foundational principle is to keep the entire operating system, including blasting and charging, as stable as possible, minimizing frequent disruptive changes. Coming to our next slide, which is about the heart of stability, which lies in the thermal control, especially managing the raceway adiabatic flame temperature or RAFT. The temperature in the raceway is extremely high, reaching around 2100 to 2200. This temperature must be regulated within a narrow window, and it must be hot enough to ensure molten iron slag are fully fluid. Typically 1500 around plus minus, we can take it as a 15 to 20 degree, or which is can be accounted as a slightly higher than 1500, but critically it must not be so hot to cause instability like irregular burden descent, otherwise known as hanging and slipping. So coming to the our next slide, we manipulate two-way input to maintain consistent flame, that is RAFT. Oxygen enrichment is a powerful tool because it increases RAFT and simultaneously increase overall production. Conversely, injecting fuel like pulverized coal, natural gas, or hydrogen in the form of moisture or steam decreases flame. This effect allows the operator to use the steam injection to smooth operation and counter humidity changes. For reliable stability, the control system must constantly correct the injectant set point for the changes in the actual hourly production rate, which is mainly determined by the amount of oxygen blown. The uniformity of the gas is critical. The gas velocity in the lower zone can be high, around 3 to 4 meter per second. Fluctuation in this gas flow over channeling must be managed, as flow exceeding the critical limit can lead to a irregular descent, hanging, slipping, uneven reduction, and fluctuation in the chemistry. Our goal is to manipulate the gas distribution to improve the smooth operation index. The effectiveness of this management is judged using permeability index, that is Q, which is a primary indicator of the furnace thermal state. The primary operational mechanism for managing gas distribution over the radius of a precise burden distribution. Modern furnaces rely on the ballast top system, which offer the flexibility to lay down material anywhere in the stock line. Uniform distribution aim to create a uniform gas flow. A key variable we control is the coke batch weight, which largely determines the thickness of the coke slit in the cohesive zone. Maintaining a stable coke slit thickness is vital for ensuring consistent gas permeability. The regularities and quality of performance fundamentally uh, fundamentally rely on the material foundation. uh, provided by the consistent raw material. Coke must not only provide fuel but also sufficient mechanical support and permeability to descending column. We must minimize the input of the problematic impurities like alkalis metal, sodium, potassium, and zinc, which are known to cause structural irregularities such as scaffolding. And daily operation uses basicity adjustment as the major way to control the ultimate hot metal quality. Now, the hearth, where the final product accumulate molten iron and in form of molten iron and slag, are collected. To ensure the liquids are free running, the final iron temperature must be kept at slightly above 1500. Crucially, any accumulation of liquid in the hearth create back pressure on the raceway. This back pressure is a major driver of the irregular burden descent. Therefore, keeping the hearth thermal system steady is a paramount for overall stability. Since the blast furnace is a continuous process, the casting regime must match the rate of production. Continuous liquid removal prevents liquid accumulation, which causes instability. The goal of zero fluctuation requires minimizing hot metal quality variation. Especially, the silicon content should fluctuate less than 0.15%. Continuous monitoring shows that the hot metal silicon content often provide an earlier indication of a cooling trend than hot metal temperature itself. Finally, even basic steps like taphole drilling should be maintained via automated control to ensure the consistency. Achieving high performance demands circumferential symmetry, meaning all wear must contribute on the circumferential symmetry equally to the process. Operators identify asymmetries by checking parameters like difference in top temperatures, heat losses, and variations in hot metal temperature between taphole. We rely on a smelting process curves which continuously record key parameters like blast volume, blast temperature, and stock line. Mastering the language of this dynamics process curves is described as necessary to dominate the blast furnace operation. The process stability is a critical for equipment integrity, with the raceway temperature reaching around 2100 to 2200. Protective measures like copper cooling steps are used to minimize heat losses on the shell. However, these steps are susceptible to significant fluctuating thermal load. Such thermal cycle can lead to a failure like cracking, water leakage, or bending of the coolers, and we are saying that is the banana effect. Designers are continuously focused on developing technologies to provide 20-year campaign life, necessitating rigorous thermal stability. So optimization is a key. So optimization is how we determine the best way to operate furnace to achieve a specific economic or environmental goal, such as lowest cost, least coke, lowest carbon emission, and so many. This typically involves utilizing matrix calculation based on the mass and energy and heat balances, while simultaneously manipulating variable like injectant quantities carefully. The optimization process is always constrained by stability parameter, primarily the requirement to keep flame within a safe operating range, such as around 2000 to 2250 degrees centigrade. Now, top gas temperature is supposed to be the most important index, and it is very critical dependent parameter reflecting the overall thermal efficiency. Two-air injection directly impact top gas temperature, which is TGT. For example, natural gas and methane injection increases top gas temperature primarily by increasing upward hot nitrogen flow. In contrast, pure oxygen injection causing top gas temperature TGT to fall. Fluidity constraints are vital for safety and efficiency, as the temperature must be high enough for modern drying but low enough to avoid damage to the gas cleaning system. So when stability fails, severe risk arises, like operationally stable loss causes irregular burden descent, characterized by phenomena like hanging, sleeping, and breathing. Safety hazard include major events like heart failure, which can result in a catastrophic run out of the molten iron and slag. If operators fail to recognize and stabilize the initial trend of instability, it can lead to a major losses and furnace shielding, which is classified as a major and very big accident. To ensure resilience, the basic operating system must remain as stable as possible. Frequent changes lead to chaos when the furnace is unstable. In the event of a sudden upset, experienced operator will take immediate remedial action, which include continuously casting, decreasing the blast volume to stabilize the furnace. Fundamentally, successful stability relies on the field operator continuously accumulating data and experience to refine and improve their operational skills. In conclusion, striving for zero fluctuation is not merely a goal but a prerequisite for achieving high performance. Stability is ensured through holistic control of the thermal state, gas flow, and liquid removal. Mastering the fundamental operation and maintaining a stable basic system allow the furnace operation to become progressively better over the long run, enabling high productivity, often ranging from 4,000 to 12,000 tons of hot metal per day, and facilitating extended campaign life, aiming for up to 20-year plus.